Hello everyone. In this video of chapter electrochemistry, we'll be talking about formulation or short notation of galvanic cells, writing cell reaction, and then I'll be talking about electrode potential and cell potential, standard potentials, and Nernst equation. Let's get started. Formulation or short notation of galvanic cell. The cell is composed of anode and cathode. And a galvanic cell is represented by a formula or short notation that includes electrode, aqueous solution of ions, other species which may or may not be involved in the cell reaction, and there is a certain convention which are used to write cell notation. Number 1. Metal electrodes or the inner electrodes are denoted by vertical line placed at the ends of the formula of short notation. The anode is written at the extreme left and cathode is written as the extreme right. That means if this is the short notation, magnesium here is anode and silver is cathode. The insoluble species, if at all are there, are placed in the interior position adjacent to the metal electrodes. For example, some gas is present or some extra thing is present. So, along with the metal electrodes, it would be written adjacent to it. The aqueous solution of ions are placed at the middle of the cell formula. Here, magnesium electrode is dipped in the electrolyte having magnesium ion. So these two are separated by this vertical line. Similarly, silver electrode, which is acting as cathode, is dipped in the solution having silver ion having a concentration of 1 molar is separated by this vertical line. The concentration of the electrolytes which is present with cathode or anode would be shown with their concentration. The double vertical lines, the double vertical line placed in between two solutions indicating that they are connecting by the salt bridge. The additional information like concentration of solution or the gas pressure should always be given along with the cathode or anode. Now, if we got this short notation or formulation of galvanic cell, by this we could understand that magnesium is anode. It is dipped in a solution having magnesium ion. The concentration of this electrolyte is 1 molar and silver is cathode and it is dipped in the electrolyte having silver ion and its concentration is 1 molar. So this is how we used to represent a cell, or you can say it is a formulation or short notation for a galvanic cell. Now, writing cell reaction. Now, consider this is a short notation of cell where nickel is anode and aluminium is cathode. At anode, nickel is oxidizing into nickel ion after removal of 2 electrons, and at cathode aluminium is accepting 3 electrons to give you aluminium metal. For obtaining net cell reaction, we need to add these two reactions in such a way the electrons which we are seeing in both the reaction should be cancelled out, and for cancelling these two electrons which are written on the different sides of the two reactions should be equal in number, and for making them equal we used to multiply with the integer to the individual half reaction. Like I will multiply by 3 to this first half reaction which is oxidation reaction, and I will multiply by 2 to this reduction half reaction. So by this I will be obtaining these two reactions, and here I will be cancelling out these 6 electrons by these 6 electrons, and this would be obtained. This would be my final cell reaction, or you can say net cell reaction. Now, electrode potential or cell potential. A galvanic cell is composed of two half cells which consisting of metal plates or electrolytes, and they are dipped in the electrolytic conductors in contact. So, at the surface of separation of solid metal and the solution, there exists a difference of electrical potential, and this potential difference established due to the electrode half reaction occurring at the electrode surface, and this potential surface difference is called as electrode potential. I can say here the potential is associated with each half reaction, be it oxidation or reduction. The potential associated with oxidation is called as oxidation potential, while when it is associated with reduction reaction, it is called as reduction potential. The overall cell potential is also called electromotive force, or EMF, is made up of the contribution of each of the electrodes. So I can say the cell potential is algebraic sum of the electrode potential, or you can say E cell is equal to oxidation potential plus reduction potential. When galvanic cell operates, electrons are generated at anode and the electrons will move through the external circuit to the cathode. The cell potential is the force that pushes electrons away from anode and pulls them towards the cathode where they used to be consumed. Now, standard potentials. The electrode potentials and the cell potential depend upon the concentration of the solution, pressure of the gases, and temperature also. And to facilitate comparison of different galvanic cell, it is necessary to measure the cell voltage under the given set of standard condition, which should be standard concentration and standard temperature also. The standard condition chosen are, we already know, 1 molar of concentration of solution, 1 atmospheric pressure of the gas, and solid and liquid should be taken in the pure form and at the temperature 25 degrees Celsius. The voltage measured under these conditions would be called as standard potential, which is represented as E0. According to our UPSC system convention, standard potential of an electrode is taken as standard reduction potential. It must be realized that oxidation potential of any electrode is numerically equal to the standard reduction potential with the reversal of sign. That means if I am talking about the standard oxidation potential of zinc is 0.76 volt. So its reduction potential would be minus 0.76 volt. And this would be called as standard potential at the standard condition. It follows that standard cell potential is written in terms of standard potential of electrodes. I repeat, it follows that standard cell potential is written in terms of standard potential. So I can say here E0 cell is equal to minus reduction potential plus E0 reduction which is happening at cathode. And if I am omitting this subscript red, so I would say E0 cell is equal to standard electrode potential of cathode minus standard electrode potential of anode. Now, dependence of cell potential on concentration, or we are talking about Nernst equation. The standard cell potential tells us whether or not the reactants in their standard state form the products in their standard state spontaneously. Or you can say we will determine the reaction is spontaneous or non-spontaneous. And to predict the spontaneity of reaction for anything other than standard concentration, we need to know the voltage of galvanic cell, which is varying according to the concentration. So, dependence upon the cell voltage on the concentration is given by Nernst equation. Let's suppose this is the general equation where these A and B are the reactants with their stoichiometry, and C and D are the product with their stoichiometry. And the cell voltage is given by cell potential E cell is equal to standard cell potential minus RT upon NF ln concentration of C multiplied by concentration of D raised to power their stoichiometry upon concentration of A multiplied by concentration of B raised to power their stoichiometry. If I convert this ln into log base 10, the equation would be E cell is equal to E naught cell minus 2.303 RT upon NF log base 10, the concentration of the products upon concentration of the reactants. Here N is the number of moles of electron used in a reaction, F is Faraday, its value is equal to 96,500 coulombs, T is the temperature in Kelvin, R is gas constant, which value is 8.314 joule Kelvin inverse mole inverse, and if we calculate at 25 degrees Celsius the value of 2.303 RT upon F, we will be seeing it is 0.0592 volt. So at 25 degrees Celsius we are replacing by 0.0592. Our equation would be E cell is equal to E naught cell minus 0.0592 volt upon N, which are the moles of electrons used in a reaction, multiplied by log base 10 concentration of the products upon concentration of the reactant. And if all the concentration, that means A, B, C, D are 1 molar, in that case log base 10 is equal to 1, its value is 0. 0 multiplied by this whole thing will be 0 and E cell will equal to E naught cell. If the gaseous substance are present in the cell reaction, its concentration term is replaced by the partial pressure of the gas. Now, Nernst equation can also be used to calculate cell potential and electrode potential. For calculating cell potential, let's suppose this is the formulation is given where cadmium is anode and copper is cathode. Cadmium is giving out 2 electrons and these 2 electrons are accepting by cupric ion to give you copper metal. The net cell reaction would be this. Here we are seeing value of N is equal to 2. So according to the formula, E cell is equal to E naught cell minus 0.0592 upon N log base 10 concentration of product upon concentration of reactant. Here we have substituted value N by 2 and cadmium is the product and cupric ion would be the reactant. We have escaped this solid because concentration of solids are taken as unity. So we removed Cu from product and cadmium from reactant because we have taken their values as 1. And if we want to calculate the electrode potential, then suppose this half cell is given here. So here is cell potential EZN is equal to EZN minus 0.0592. The value of N is equal to 2 because 2 electrons are getting consumed. Log base 10 1 upon zinc ion. 1 we have taken because zinc is solid here. So 1 upon zinc ion. So on reversing this, we will be getting E zinc is equal to E naught Zn plus 0.0592 upon 2 log base 10 concentration of zinc ion at 25 degrees Celsius. This is how we used to calculate the cell potential and electrode potential. Thank you.